Hello friends, in this video we will see the vector representation. Vector representation means how AC values can be represented in different forms. Let us begin. Vector representation means the different forms in which I can now show alternating values. Alternating values means alternating current or alternating voltage. For example, I can have alternative voltage V of t. I can show like this, or I can show it like this, or I can have another alternating values like this. As you can see, there are three types of AC values which I have drawn. All of them are not having same phase, meaning that if I take this as a reference, then this is lagging. Whereas if I take 0 as a reference, this is leading. It means I can represent my vector values, that is nothing but alternating values, graphically. This is way one, that representing vector values with the help of graphics. So this is first way, representing AC values using graphical technique. See, when it comes to processing or mathematics, this graphical representation is not okay for us. We need a particular representation in terms of mathematics. For that, we have various forms. We will see what are those. The second form is called as sinusoidal form. First form we have already seen as a graphical form. The second form I am going to show you, sinusoidal form. For example, I can represent a particular AC signal, let's say V of t, it can be I of t also. Let's say Vm1 sine of omega t plus phi 1, or else I can have another signal V2 of t as Vm2, let's say sine of omega t minus phi 2. Positive phase indicates it is leading with respect to reference, whereas negative phase indicates it is lagging with respect to reference. So first example shows it is leading and second example shows it is lagging. So this was signal number 1 and this is signal number 2. Let me tell you, sinusoidal form, it's okay that looking at sinusoidal form, we come to know what is a magnitude, we come to know what is a frequency, as well as we understand whether it is leading in phase or lagging in phase. Otherwise, when it comes to calculation part, you know the fact that operating with sine and cos becomes quite difficult because one has to remember all trigonometric formulas. That's the reason why we go for another form which becomes easy for calculation point of view. Let's see what is the third form now. Third form is nothing but polar form. Polar form means it is in this form, R at an angle of phase, where R indicates magnitude and this indicates phase or phase angle. Now the question arises, why do we really need a polar form? Answer is very simple. Suppose if you want to multiply or divide the signals, for example, if I wanted to do multiplication of two signals or division of two signals, because it is all about signal processing. For example, you can add these two signals or you can subtract these two signals, you can multiply, in fact you can divide also. So for multiplication and division, it is 100% sure that sinusoidal form is not appropriate. For that we go for polar form calculations. You will understand why I am saying so. So we had signal 1, if you remember. In sinusoidal form we have written it as V1 of t equal to Vm1 sine of omega t plus phi 1. Whereas signal number 2 we have defined V2 of t as Vm2 sine of omega t minus phi 2. Therefore, as I said, these two signals are not in appropriate form for multiplication and division. Better to convert them into polar form. How to convert them into polar form? It is very easy. V1 of t, now we will write as V1 vector because they are vector values. Of course, vector value is something which has got magnitude as well as phase. So V1 vector I should represent as magnitude first. What is the magnitude for V1 of t? It is Vm1. So I can write Vm1 at an angle phase which is phi1. Sometimes we have tendency to write magnitude as RMS value. So we know RMS value is nothing but peak value by root 2. So sometimes you will see V1 vector we can represent as Vm1 by root 2, that is RMS value at an angle of phase phi1. In a similar way, we can represent V2 vector as Vm2 at an angle of minus phi2, because it should be expressed in terms of magnitude and phase. For V2, magnitude is Vm2 and phase is minus phi2. So we have to represent even phase along with its original sign. Finally, what was the purpose? The purpose, when you have to multiply or divide, polar form becomes quite easier. We will see how. So purpose should be very clear: to multiply and divide alternating values. But how do we do that? Let's see. Let's recall V1 vector and V2 vector in polar form. We had V1 vector as Vm at an angle of phi1 or Vm1 at an angle of phase phi1, and V2 vector was Vm2 at an angle of minus phi2. Now let's say if I want to multiply these two signals, that is V1 vector multiplied by V2 vector, then it becomes Vm1 at an angle of phase phi1 multiplied with Vm2 at an angle of phase phi2. When you multiply two vector values, their magnitude gets multiplied and phase gets added. Final answer is Vm1 into Vm2 is a final magnitude and final phase will be phi1 plus of minus phi2. So in a way it becomes phi1 minus phi2 only. So as you can see how easy it is to really multiply two vectors. And imagine if they would have been in sine form, it would have been in terms of Vm1 sine of omega t plus phi1 multiplied by Vm2 sine of omega t minus phi2. For that you should know what is the formula for sine of a plus b and sine of a minus b, and thereafter you need to expand them, and you know what it really takes to really expand trigonometry form. That's the reason why when you really want to multiply, it is always better to go for polar form. Not only for multiplication but even for division, polar form is appropriate. We will see how. Suppose you want to divide two signals, that is V1 vector by V2 vector, then it will be Vm1 at an angle phase 1 divided by Vm2 at an angle of phase 2. When two polar values are divided, their magnitude gets divided but angles get subtracted. Therefore, the second signal had phase as negative. Therefore, now it became Vm1 by Vm2 at an angle phi1 minus phi2. Therefore, now it has become Vm1 by Vm2 at an angle phi1 plus phi2. Please remember, in the division, angle really gets subtracted. Here it becomes addition because phi2 was negative and negative became positive. So this is how we use polar form for multiplication as well as division, or for multiplication and division of alternating values. Let's go for the next form. So let us begin with rectangular form now. If you remember, we had signal 1 as Vm1 phase phi1, as well as we had signal 2 like this, Vm2 having phase as minus phi2. Let me tell you, rectangular form is nothing but a complex form, which is nothing but x plus jy form, which will have real part and imaginary part. For example, if r phase is given, this is nothing but a polar form. If you convert into rectangular form, it becomes x plus jy, where value of x and value of y is given as x is nothing but r cos phi plus j as it is, y is nothing but r sin phi. This is how we convert polar form to rectangular form. In a way, I can represent my signal 1 in rectangular form like this: Vm1 cos of phi 1 plus j Vm2 sine of, we should say Vm1 only because it belongs to signal number 1. Whereas for signal 2, I can represent it as Vm2 cos of minus phi 2 plus j Vm2 sine of minus phi 2. We know the fact that cos of minus theta is cos theta, but sine of minus theta is minus sine theta. So I can rewrite this as Vm2 cos of phi 2 minus j Vm2 sine of phi 2. So what I can see is signal number 1 is having real part is Vm1 cos phi 1. Let me represent real part for signal 1 as x1 plus j. As you can see, Vm1 times sine phi 1 is imaginary part for signal number 1. Let me represent imaginary part for signal number 1 as y1. Finally, you have signal number 2. Signal number 2 was Vm2 cos phi 2. It is nothing but real part for signal number 2. Let me represent real part as x2. In between you have negative sign j. Remaining is imaginary part for signal number 2. Let me represent imaginary part with y2. Finally, we have signal 1 and signal 2 in rectangular form like this. We have signal 1 as x1 plus j y1, whereas signal number 2 is now represented in rectangular form like this, x2 minus jy2. Now what is remaining is the purpose why we need another form, that is rectangular form. Purpose is very clear. Purpose is to add or subtract two signals. So for addition or subtraction of alternating signals, we prefer rectangular form. You will understand why it becomes really easy for addition and subtraction. For example, if I want to add signal 1 with signal 2, it means it is addition of two complex number x1 plus jy1 will be added with x2 minus jy2. You know the fact, when two complex numbers are added, real part gets added, imaginary part gets added. In effect, we have final value as x1 plus x2 plus j. If I take common, it is y1 minus y2. Whereas if I subtract signal 1 and signal 2, that is signal 2 from signal 1, I will get x1 plus jy1 minus x2 minus jy2, or I can write it as x1 minus x2 plus j. If I take common, it is y1 plus y2. So as you can see, addition and subtraction becomes very easy because real part we have to take together, imaginary part we have to take together. Let me make you very clear, in polar form addition and subtraction is not possible. For addition and subtraction you need rectangular form. For multiplication and division, even rectangular form will not be appropriate. I don't say multiplication or division is not possible, but it is quite tedious job. That's the reason why for multiplication and division we should go for polar form. For addition and subtraction, we go for rectangular form. Finally, we will see the relation between polar form and rectangular form, and we will conclude this lecture. So first of all, we will understand how to extract rectangular form if polar form is known. So let's see how to get x plus jy from R phase. That is, extracting rectangular form from polar form. It means this is given and this is required. In that case, we have already seen this actually. It is x equal to r cos phi and y is simply r sin phi. Once you get x and y, just substitute in this expression. Now we will see how to convert rectangular to polar. In rectangular, we have x plus jy form, and in polar we have R phase. It means now this becomes given and this becomes required. In gate calculator do not support like a normal calculator where you easily convert polar to rectangular or rectangular to polar. This traditional method should be known to you how to convert rectangular to polar and polar to rectangular. We will see. You know the fact R is magnitude. How to get magnitude of the rectangular form? Very easy. R is under root of x square plus y square, that is real part square plus imaginary part square. And how to get phase? It's very simple. It is tan inverse of imaginary part upon real part. As you can see, imaginary is y, real is x, so it is simply y by x. Once you get r and phi, just substitute in this form, that is r at an angle of phase, and you get straight away polar form. I'm sure you have understood rectangular form, polar form, how to convert a rectangular to polar, polar to rectangular, what are the applications of polar form, what are the applications of rectangular form. Thank you.